Good morning, students. Myself, Vijay Shankar from BC Department, Chevrolet Engineering College. Today, we are going to discuss about the types of sampling. Another sampling is a flat top sampling. Third sampling, flat top sampling or the rectangular pulse sampling. Flat top sampling or rectangular sampling, my students. See, what is here the flat top sampling means this is also practically possible method. Which is not practically possible method. Instantaneous sampling is not practically possible method because there is this one. The impulse sampling method is not practically possible. Ideally, it is okay. And natural sampling is also overcome the two limitations what we have in the instantaneous sample, pulse width and the interference is overcome by using the natural sampling. And another sampling is that the flat top sampling or the rectangular pulse sampling. This is also practically possible. Natural sampling is a practically possible and the flat top sampling is also practically possible function. Okay. The circuit looks like but easy method to get the flat top samples. Means why I am saying it is a flat top. See, in the natural sampling, there is the cutoff here. But in this, it is a flat. For every sample, there is a flat amplitude is there. Okay. And there is an amplitude distortion. In this, there is some amplitude distortion is there. That we can say that is an aperture effect. We are getting the amplitude distortion in the flat top. That amplitude distortion, we call it as a aperture effect. That aperture effect we can rectify or reconstruct by using the equalizers. Okay, my dear friends. Let us see. There is two switches are there. One is a sampling switch, another one is a discharge switch. Discharge means so the capacitor is discharges and the charging when it is on and off. When the sampling switch is on, means the signal x of t, I'm convoluting with the h of t. Actually, you see, in the instantaneous sampling, the x of t signal is sampled with the delta function. For every signal, there is a t and any ts, 2ts, and so on. Okay, is a delta function. After the sampling, the signal is getting like this. If it is increases at the increases and decreases at the decreases, wherever it is. This is x of t multiplying with the delta function. After multiplying, we convolute with the impulse function. Means the impulse having a width is there. That width for every sample, there is a width we'll get with the h of t is convolute in the flat top side. The delta of t, the signal is convolute. This signal is a convolute with the h of t. Then we'll get the impulse signal is a h of t only. Whenever there is a convolution with any delta function, the same signal will get, but with having the width is there. The width of the pulse is a flat top sampling and the natural sampling is increased to reduce the transmission bandwidth. Okay. Here, the top of the sample remains constant, which is equal to the instantaneous value of the baseband. The top of the sample remains constant, which is equal to the instantaneous value of the baseband. Got it, my dear friends? Means if I am taking the x of t signal, multiplying with the instantaneous sampling, the delta of t signal, getting is sampled version of the x delta of t and is given to the h of t signal getting the y of t. Okay, getting the y of t or the s of t signal. Let us take this as s of t. So what is the s of t? The y of t is equal, let us take, they are saying here the y of t only. And this x delta of t as s of t. So convolution between these two functions. S of t is convolute with h of t. Got it, my students? So this is a y of t. So x of t signal, you are taking the continuous time signal as the impulse train delta of t, multiplying the two functions, getting of s of t. And this s of t signal is given to the h of t, passes to this h of t. Okay, then we'll get y of t is equal to s of t with the convolution of h of t. Got it, my students? So s of t, the h of t with the convolution of what is the s of t? We already know the signal x delta of t is x of t, the instantaneous sampling. X delta of t is equal to the sum of n is equal to minus infinite to infinite x of t delta of t minus n into ts. This we know, the my dear students. So convolute with x of t. Applying the Fourier transformation on both sides. What is the y of t? Is a y of f. What is the h of t? H of f. And the Fourier transformation of this function. We know the Fourier transformation of this function is as a time domain, x of f is equal to, we got fs into sum of n is equal to minus infinite to infinite x of f minus n into fs. Minus n into fs. You see here, h of f and the x of f, and this total function is 1 by ts is fs, sum of the delta function, delta of f minus n into fs. Got it, my students? Okay. Now, what is a h of f? H of f is a sinc function. We already know that is a x of f function. Now, what is a h of f function? Let us take the h of f, means you'll get from the h of t only. Having the duration of 0 to t, amplitude is a 1 as a h of t. Is a signal, my students. So what is a h of f? H of f is equal to integral minus infinite to infinite h of t into e power minus j omega naught, j omega 2 pi f into t dt. So what is the h of t? Its amplitude is a 1 in the duration of 0 to t. Take the 0 to t here. 1 e power minus j 2 pi f into t dt. Got it, my students? Okay. Now we can apply the integral the e power minus j 2 pi f into t small t by the t coefficient is a minus j 2 pi f, with upper limit is a t, lower limit is a 0. Got it, my students? Now simplify here the 1 pi minus j 2 pi f multiplying with e power minus j 2 pi f into small t is replaced here the capital T minus e power minus j 2 pi f into 0. Here there is a minus is there, multiplying the minus and swap these two functions. Then it becomes a 1 by the 2j pi f, and the negative becomes a positive, that is nothing but 1 minus e power minus j 2 pi f into t. Now I'm modifying this function as 1 by 2 pi f 2j pi f minus 1, j 2 pi f. 1 we can write as e power minus j pi f into t, e power plus j pi f into t, minus and plus is becomes e power 0 only, that is a 1. Again, I am writing these also, e power minus j pi f into t, e power minus j pi f into t. So bases are same, we can add the powers, minus j pi f into t minus j pi f is a minus j 2 pi f into t. In these two equations, take the common of e power minus j pi f into t, you can take as a common, and denominator there is a j 2 pi f, and after taking the common of e power minus j pi f into t, we have e power j pi f into t minus, here another e power minus j pi f into t is there, pi f into t, and bring this as a 2 by j here. It becomes of e power jx minus e power minus jx by 2j. Got it, my dear students? So it becomes of e power minus j pi f t whole divided by the pi f. It becomes sine jx pi f into t. Pi f into t. Okay. Again, multiply and divide with the capital T. Here I am multiplying the capital T and dividing with the capital T. Sine pi f t and the sine pi f t. We know sine pi theta by the pi theta becomes sinc theta. Sinc theta. So modify this equation as t e power minus j pi f into t sine pi f t, and divided by this there is a pi f t. So sinc EFT. Sinc EFT. Got it, my dear students? The total function now, the h of f is equal to whatever we start, that is the h of f is equal to t into e power minus j pi f t sinc EFT. Got it, my dear students? See here, we got the same thing. T e power minus j pi f into t sinc EFT. The h of f is equal to t e power minus j 2 pi f t and sinc EFT. Got it, my dear students? That t I am replacing as a tau. So t e power minus j 2 pi, not the e power j 2 pi is there. It's only the pi f, my dear students. So e power j pi f into t sinc f into t. Therefore, the s of f is equal to h of f is replaced. H of f you can replace the s. Y of f is equal to h of f into the x of f function. That is a ts or 1 by ts or the fs, sum of n is equal to minus infinite to infinite. X of f minus k into n fs. Okay. We know that is a function, that not the k. Instead of k, I am substituting the n. Fs into sum of n is equal to minus infinite to infinite. X of f minus n into fs. This is x of f and is multiplied with the h of f. What is the h of f? We got fs into t, not the fs, the t into e power minus j pi f into t sinc EFT multiplying with the fs, sum of n is equal to minus infinite to infinite, x of f minus n into fs. Okay, this is a total function of s of f is equal to the frequency domain, or s of f is equal to, finally you can write as fs into t e power minus j pi f into t sinc eft, the sum of n is equal to minus infinite to infinite, x of f minus n into fs. The final output of the x of s of f. Okay, you can call it as a pulse amplitude modulation or sample and hold circuit with the period is of tau or the t, and the sampling time is a ts. Got it, my students? So these are the three different types of the samples or samplers. One is the instantaneous sampling, which is not practically possible condition because of the pulse width is 0 and having noise interference. That is overcome by using the natural sampling, and it is a practically possible. And another one is a flat top sampling, it is a rectangular pulse sampling. It is also practically possible, and it having there is a amplitude distortion will get in the flat top. That is avoided by this effect is nothing but aperture effect that can be reconstructed by using the equalizers. What it matters, students? The comparison here, ideal instantaneous sampling, natural sampling, and the flat sampling. The principle of sampling is it uses the multiplication by an impulse function. It uses the chopping principle, including the multiplication also. It uses the chopping principle. It uses the sample and hold circuit. Okay, the circuit is a switch, and in the flat top sampling there is a two switches. One switch is a sampling switch, another switch is the charging and discharging of the capacitor. When the discharge is charging means it goes from 0 to some volts, 10 volts, again 0 to 20 volts, 0 to 30 volts, like that, and decreases from 10 to 0, 20 to 0, 30 to 0, so on. Okay, like that we'll get the output. And waveforms, the sampling and here the waveform is look like this, the natural sampling. Like this, and in the flat top sampling, it is also like this. And realizability, it is not practically possible. The instantaneous is not practically possible. Use it practically and use it practically, the flat top and the natural sampling. And sampling rate, it tends to infinite and satisfies the Nyquist state, and it also satisfies the Nyquist state. It's a finite values. Noise interference, here there is, I told that why it is not practically possible means the noise interference is maximum. So it is in the natural sampling, it's a minimum and is a maximum here. Time domain representation, x delta of t is x n into ts delta t minus n into ts, and is in terms of the sync functions. Frequency domain, x delta of f is equal to fs into x of f minus n into fs, and here the s of f and s of f with the sync functions. What it matters? So very, very important. The comparison of instantaneous sampling, natural sampling, and the flat top sampling. The principle is it uses the multiplication in the impulse function. It uses the chopping principle. It uses the sample and hold. Okay. And the circuit diagram, it is having the switch, and in the natural sampling also having the same, the switch we have. Just like this, the input signal having the switch 1 and the switch 2 here. Whenever the switch is 1 is on, the x of t, the input signal will get the x delta of t here. Whatever the same thing in the instantaneous sampling, but there is a chopping occurs in the output sampling. And in this circuit, there is a 2 switches. One switch is a sampling switch, and another switch is there in the shunt, the charging and discharging of the capacitor. Why it is a charging and discharging of the capacitor means it holds and the sample. Understood? The waveforms realizability, it is not practically realizable, it is used practically realizable, and it is also practically useful. Sampling rate tends to infinite and it satisfies an IQ state, and it also satisfies an IQ state. Noise interference is maximum in the instantaneous and the minimum in the sampling, and the maximum in the flat top also. We have the time domain function and the frequency domain equations. Okay, my dear students. It's a very important, my dear students, a comparison of sampling. The 3 types, instantaneous and the natural sampling and the flat sampling. Okay. The next is the effects of undersampling. The effects of undersampling, nothing but aliasing. So aliasing is undersampling. The Fs is less than the 2 FM. Call it as undersampling. Undersampling. And Fs is greater than the 2 FM. Call it as oversampling. And Fs is equal to 2 FM. It's equal. Okay. The undersampling, we are getting the aliasing effect. Aliasing effect. To reconstruct the signal in the oversampling, we are using a practical low pass filter to recover the original signal. And for the equal condition, Fs is equal to 2 FM, we use the ideal low pass filter to reconstruct the signal, recover the original signal from the sampled version. Okay. So what are the effects under the undersampling aliasing? When a continuous time band limited signal is sampled at a rate lower than the Nyquist rate, nothing but Fs is less than the 2 FM, then the successive cycles of spectrum Y of F of a sampled signal Y of T overlap with each other. See here, there is a overlapping occurs here, and for every spectrum, there is a overlapping occurs. Okay. As the signal is unsampled after the less than undersampled, when Fs is less than the 2 FM and same amount of aliasing is produced. And some amount of aliasing is produced. Aliasing is the phenomena in which the high frequency component, see here, this is a high frequency component in the frequency spectrum of a signal takes identity of a low frequency component in the spectrum of the sampled signal. Aliasing is a phenomenon in which a high frequency component in the frequency spectrum of a signal takes identity of a low frequency component in the spectrum of the sampled signal. The next point is, due to aliasing, it is not possible to recover the original signal x of t from the sampled signal of y of t by low pass filter. It is a very important point. These two. Due to the aliasing, it is not possible to recover the original signal x of t from the sampled signal y of t by the low pass filter. Next point, the signal is distorted, means how it is getting like this. Here there is any, you'll get the distortion, then the signal look like you are not getting this part. Okay, sorry, I will get how if the signal is band limited to FM hertz, there is a overlapping at this, like this, then the signal will get like, signal is distorted. This part is distorted here. It's not getting the full. Got it? Due to the aliasing, it is not possible to recover the signal, original signal x of t from the sampled signal y of t by the low pass filter. The signal is distorted and the information signal containing a large number of frequency divided by the sampling frequency is always a problem. The signal is first passed to the low pass filter, which blocks all the frequencies above FM hertz, band limited of the original signal. This low pass filter is called the pre-aliasing filter. It is used to prevent aliasing effect. To avoid aliasing, pre-aliasing filter must be used to limit the band of frequencies of the signal to FM hertz. The sampling frequency must be selected such that Fs is greater than or equal to FM. Due to the aliasing effect, there is a distortion occurs, and that signal is used to recover the signal by using the pre-aliasing filter must be limited to the band frequency signal is selected such that Fs is greater than or equal to 2FM. Okay. The low pass filter is a pre-aliasing filter. It is used to prevent aliasing effect. It is used to prevent the aliasing effect. To avoid the aliasing effect, we can select Fs is equal to 2FM or Fs is greater than or equal to 2F. Understood, my students? So in this sampling, so very important is what is the sampling? What is the sampling? The examination point of view, and state and prove the sampling theorem. State and prove sampling theorem means the construction and the reconstruction. Construction of filter, construction of the signal, and reconstruction of the signal. Okay. And types of sampling. One is ideal sampler. Second one is in the last class we discussed ideal sampler, and the second one is a natural sampling. And third one in the today's class we discussed, that is a flat top sampling. Flat top sampling. Okay, and comparison of samplings, sampling techniques, and aliasing effect. Aliasing effect. Okay, the last top. Okay, my dear students, with this the theory part of the sampling is completed. Third unit, I think.